Welcome back to CST432, Microprocessors and Embedded Systems. Today we will look at how to apply what we have learned in terms of the language instructions in developing our first robotics software. So this is the first step, part 2. Key concepts we will cover today includes the line following basics, meaning how does a robot track a line painted on the ground to achieve the goal of following the line towards a certain objective. Secondly, we will look at how we can implement a min-max algorithm, which is to determine the minimum and maximum values in a group of input values. And we will also look at the efficiency of various flow control statements in achieving the goal of an efficient implementation. Finally, we will use what we have learned to implement a line follower robot. So how do we implement a line following robot? First, some basics. We note that on the tripod there is a light sensor that has an LED light that generates a light beam to detect the intensity of the reflection. In our case, the reflection comes from the ground, which has a painted line of usually of black color on it. So when the tripod uses the light sensor, it will detect three cases. The first case is where the light sensor is located inside the line and it has a very dark or black color reflection. The second case is when the light sensor is on the edge of the line and the reflection is a mixture of light and dark colors. And finally, the third case is where the light sensor is totally outside of the line and is reflecting the color that is not a black color. We should note that analog values read by the light sensor can vary, and it depends on the surface, reflectivity, and the color of the markings. In other words, you need to do some tweaking or tuning of the light sensor before we can make use of the readings reliably. Now, the range of values can also be returned for each case, and in order to sort out and understand whether a light reading belongs to the case where it's on the line, on the edge, or outside of the line, we should try and determine the minimum and the maximum values of these readings to see if they match a given case. So for the cases given here, the color that we may detect for inside the line will be black, where we get high readings from the light sensor. If the robot is on the edge, and the color to be detected will be either black, white, or even gray at the boundary. And the readings that we get will be intermediate. Finally, if it's outside the line, the color that we will detect is white, and the readings will be low from the light sensor. We will first investigate the abstract minimum-maximum algorithm. We assume that the input values are normalized, meaning that they fall into a range of 0 to 100%. In this case, we can use an algorithm that works with 8-bit values, since 8 bits cover the range from 0 to 255 for unsigned numbers. Secondly, we assume that all input values are already in a memory array, and we only need to concentrate on the minimum and maximum determination process of the algorithm. Finally, we will focus on retrieving values from memory arrays and determining the minimum and maximum. So we will not concern ourselves at this point with how we can actually read the value from the light sensor. First, we look at the min-max pseudocode. We will look at how we can implement the min-max algorithm using a for loop. Given that we have n 8-bit unsigned numbers in an array of readings, we first set the minimum and maximum values to the extreme ends, where we set maximum to 0 and minimum to 255. This ensures that the subsequent readings will force the minimum and maximum values to a real reading instead of being stuck at either end of the scale. Then we will iterate through the number of readings to determine the minimum and maximum values that we have encountered. So in this case, using a for loop, we will have a counter going from 0 to n minus 1. Remember that the index starts from 0 in C. Okay? And then if the readings in the array at location counter, index counter, is less than the minimum, we will then update the minimum value to this current reading. However, if the reading is greater than the maximum, we will also update the maximum to the current reading. And we'll iterate through this array until we are done. Now, when we're implementing a for loop in assembly language, we find that it is not so straightforward. We can rewrite the for loop into a while loop. This is semantically equivalent, meaning that it does exactly the same thing as the for loop. So given the previous algorithm, we will just change the for loop into a while loop where we check the value of counter to be less than the total number of values that we have given by the variable n, and we'll just iterate through the loop as before. We can do one more optimization. Because the check at the end of the while loop in the last version compares the value of counter against the value n, this incurs some additional overheads. Now we will understand why this is the case later. But for now, let's just say that we will look at how we can do the comparison against 0. So when we want to rewrite the loop in this way, we will use a while loop using the comparison at the end of the loop rather than at the beginning of the loop. So in this case, we will decrement the counter at the beginning of the loop to come up with a correct index for the array, and then do the comparisons for min and max to determine min and max, and finally we will do the comparison against 0 to determine whether we would need to repeat the loop or terminate the loop. Here we will look at the assembly language version of the algorithm. Given here in the comments is the exact same pseudocode as given in the optimized version. The reason why we want to compare counter against 0 is because the comparison against 0 is implicit in some of the arithmetic operations that we do. We do not need to spend an extra instructions in order to force a comparison against 0. Next, we look at the data array declaration. Here we have three different data items. The first is readings, which is an array of byte size having the values 70, 3, 95, 0, and 23. These are just some sample values that we use for illustration. Secondly, we all have the value for min and max, which are also 8-bit values declared in the data section of the program. Next, we will look at the register allocation. R0 is used as a temporary value storage or scratch register. R1 is used to store the value of counter. R2 is used as an array pointer to the readings array. R3 would be used to store the minimum value, whereas R4 will be used to store the maximum value as we iterate through the number of readings. First, we will start at the label start. The first instruction is to initialize R4, which is the maximum value, to 0, and R3, the minimum value, will be initialized to 255. Next, we will initialize the R1 register, which is keeping the value of counter to the number of items that we have given by the constant n. And finally, we will initialize R2 as the pointer to the array readings. Next, we will look at the loop structure itself. The first instruction in the loop is to subtract 1 from the value of R1, which is the counter. So from being a counter, this will become an index into the array, and we use the index address mode where we use R2 as the base register and R1 as an index into the array to retrieve the reading for into R0. Next, we will check the value of reading against the minimum and maximum values. The compare R0 R3 will allow us to check it against the minimum value. Is it less than R3? If it is, we will use the conditional execution instruction move low to copy the value of R0 into R3, which is the new minimum. Next, we will perform the check for the maximum value. Similar to the earlier section, we will compare R0 against R4, which is the maximum value. Is it greater than R4? If it is, then we use the conditional execution instruction move high to copy the value of the current reading into the new maximum value in R4. Finally, we check if we have reached the end of the loop. We compare R0 against the value 0, and if it is not 0, we will loop back to the label loop. If not, then we will fall through to the next instruction. Finally, we would like to store the values for min-max from the register into memory for later use. In this case, we will load the address pointer for min into R2. And knowing that min and max are in consecutive address locations, we will use the index addressing with a constant offset to access each of these memory locations in turn to store the value of min and max into memory. Now we will look at how we can make use of this algorithm to implement the line follower robot. The line follower robot is based on the Lego Mindstorm Tribot, and it uses a single line sensor to follow line markings on the floor. Given that it is inside a line, it will go straight. If it is on the edge, it will rotate slowly. But if it is outside the line, it will try to rotate quickly to reacquire the line. Now, as I mentioned previously, we need to calibrate the line sensors when we want to implement this robot. And some example code is found in the NXOS ARM debug system directory. It is found under the system subdirectory as a tribot/line follower program. We will first look at the behavioral diagram for the line follower robot. We have an input from the line sensor, which are reading values. This will then be passed to the algorithm called follow line, which is also known as a behavior, which indicates what it's supposed to do to follow a line, which will then program the appropriate settings to the motor controller to control the left and right motors, whether to go straight, turn, or rotate. So this is the source code for the line follower program in NXOS ARM debug. At the bottom of this slide, you see an important definition. It is currently specified as undefined debug min-max. Now, if you want to calibrate the light sensor, we will need to change it to define debug min-max in order for the program to run a different algorithm compared to what the default will be. Next, we will look at the various settings or values we use for determining whether the sensor is detecting a line on the edge or outside of the line. And these values, as mentioned, must be calibrated. So if we define debug min-max, the program will no longer operate in the normal way, but instead enter debug mode, where the values read by the light sensor is displayed on the LCD. And we can collect these values and later adjust the values defined here to reflect the actual settings of the board or the system that we need. Next, there are some constants used to define the speed of the motors for going straight, for rotating slowly, and rotating quickly. Now, if you set too high a speed, we can cause the tribot to overshoot, especially when we think that we are on the line. But if you move very quickly, the robot can suddenly find itself exceeding the line on the marking on the floor and then be on a non-marking area. Next, we define the variables we need. It's similar to the previously seen abstract algorithm. We define a constant value n, and using this value we can then allocate space for it or an array for it using the dot space directive for the assembler. Here we have a pre-allocated space of initialize to value 0 as a default. Here we see the min-max algorithm converted into a subroutine. As we mentioned previously, we are using R0, R1, R2, R3, and R4 for the purposes of the algorithm. Now, R0 to R3 are defined under the AAPCS as being scratch registers or parameter passing registers, which do not need to be preserved. However, R4 is a register that is often used by the calling routine and is expected to be unchanged after the routine returns. Consequently, we will need to push the value of R4 into the stack to preserve it. We also need to push the value of the return address in the link register to enable us to call any further subroutines if necessary. Finally, at the end of the routine, we will restore the value in R4 and return execution to the calling routine using the pop instruction, which retrieves the value of R4 into R4, as well as to set the value of the program counter to the value that was in the link register previously. This will then return execution to the calling subroutine. Here are some supporting functions. We define some tone generation functions called plip, plop, and plap to allow us to generate a tone to quickly determine whether we are on the line, on the edge, or outside of the line. Next, we have a supporting routine to turn on the LED. The step of turning on the LED is a separate step from determining the light reading from the sensor. So this is a supporting routine to enable us to turn on the LED at the beginning of the robot's execution. Similarly, we have a routine to turn off the LED, which is used at the end of the robot's execution when we are done. Here we have some supporting routines to help display the status of the robot on the LCD. In this case, black detected is used when we have detected the black color, which means that we are on the line, and the display will be updated to indicate this fact, as well as the state of the robot, known as robot state, will be recorded into this variable that we are on moving forward since we are on the line. We note that there is a comparison here where we check whether the robot state is already programmed to forward. If it is already forward, we will skip the updating of the motors and instead we'll exit this routine. If the previous state is not in the forward state but instead some other, whether it's rotating left or fast rotating right, we will update the motor speed and the for both the left and the right view to move forward at the same speed using the forward speed setting. The next routine, white detected, is used when we are no longer following a line but have turned wheel off course somewhere. In this case, we will program the wheel to not move on the right view, but instead we will rotate fast on the left view. This will hopefully bring us back onto the line. The third case is when we have detected an edge, meaning that we are about to veer off course. In this case, we will program the robot to not move the left view, but we will turn the right view slowly so that we hopefully will reacquire the line and stay on course. Finally, what happens when we are not sure what reading we get? In this case, it's safest just to stop the robot and not do anything. So when we have detected an unknown color, we will then stop the motors and let the robot rest. Here we have the initialize robot routine. At the beginning, we will configure the sensors. For the line follower, we actually only need to initialize the light port or the light sensor. However, we also initialize the touch port here, which is used later in a different robot in future. Next, we will initialize several of the registers with the settings or values that we need for the operation of the program. Next, we have the shutdown robot routine. This routine is called at the end of the execution of the program. Since we had defined an unknown detected subroutine earlier that stops the rotation of the motors, we reuse it here to perform the same action, which is to stop the robot from moving further, and after that we can shut down the robot. Here we come to the main robot routines. Here we notice that there is an if define, if def, which is using enable breakpoints to control whether we would pause the execution of the program to wait for a connection from the remote debugger when we are trying to develop this program. Now by default, an operating robot would turn off enable breakpoint so that it will continue execution without any stopping. However, if we are trying to update or modify the program, we will define enable breakpoints and the robot will stop at the debug breakpoint arm macro, which will allow us to connect the debugger to the robot, and finally, after we start up the debugger, we will then break at the next location highlighted, which is at the break label. Then we place a no operation instruction to allow us to break safely. So the first thing we do when we start up the program is to initialize the robot, which calls the init robot subroutine defined previously. Next, we enable the LED light so that we can start reading values from the light sensor. We use R8 as the iteration counter. This gives an upper number to the number of iterations of the main loop that we will execute in the robot. This allows us to prevent the robot from running indefinitely and running down the batteries. Next, we will try to gather some light sensor readings. Here, we use R6 as the index register. Given that we initialized it previously to the size of the array, we need to decrement it by 1 to convert it into an index. And using the index, we will then retrieve the light sensor reading from the sensor itself and store it into this array at the given index. Now here we need to insert a 3 millisecond delay because of the requirements of the AVR A to D converter. This allows us to retrieve a correct, accurate reading from the A to D converter, because if you try to read any faster, the values that is returned will be invalid. Now, as long as the number of readings that we have collected is less than the size of the array, we will not try and update the minimum and maximum values. Instead, we will skip the minimum maximum value algorithm and continue to perform the other tasks of the robot. Once we have collected enough readings, we will then call the min-max subroutine to confirm the values for minimum and maximum for us. We will also need to reset the counter to the original value so that we can collect a new set of readings in future. Finally, we can define a breakpoint here to allow us to inspect the values in the array if we chooses. Now comes the interesting part. Here, we want to check the values we have calculated for the minimum and maximum values of the readings and compare it against our list of or the range of values that we have defined previously. Now, as I mentioned previously, if we have defined the debug min-max variable, that we would then execute this portion of the program to display the minimum and maximum values that have been read. However, under normal operating process, this portion will not be executed or compiled. Since we have retrieved the value for min into R0 and max into R1, we can now compare it against the range of possible values to determine whether we have a white, an edge, or a black detection. The first case, when we check against white, we will compare the R0 to see if it is within the range of white min and white max. If it is less than white min or greater than white max, then it would be considered to be out of range. If it is less than white min, we detect the case where it is unknown reading. If it is greater than white max, then we will skip it to go on to check whether it is an edge. However, if it falls within this range, we will consider that we have detected a white reading from the light sensor, and we will perform the appropriate action. Next is the case of where we try to detect whether the readings are an edge. Again, we will compare the minimum value against the minimum value defined for an edge reading and the maximum value against the edge max constant. If we fall within the range, we will have detected the edge. If not, then either it is an unknown value if there's a gap in the values between white max and edge min, or else we will need to check whether it is a black value. Similarly, we check it against the range of values for black. We compare against black min and black max. If it exceeds the value of black max, then definitely we do not know what value it is and we mark it as an unknown value. Similarly, if it is less than black min and there's a gap between the edge max and black min, then we will again flag it as an unknown value. However, if it falls within the range, you will have detected a black light reading, and we will then move forward in a straight line using the black detected subroutine. If it is not a recognized light reading range, we will flag it as being an unknown range, and we will stop the motors and let the robot wait until further intervention by the operator. When we encounter the maximum iteration for the robotic software operation, we will then shut down the robot and quit the program. Final routine, NX program shutdown, will shut off the NXT to allow us to conserve power. Here is an additional question to think about. What changes do we need to make to the min-max algorithm if the list of values to be processed consists of signed numbers, meaning positive and negative values, instead of the unsigned numbers that we have been working with previously? Here we will see the calibration process. I have defined a different program that will allow us to look at the values read by the light sensor when you define the debug min-max variable. If we place it onto the white part of the track, we see that the min-max value will be changing to a certain value given here as 47. Okay, there's a delay involved when in the sensor updating of the LCD to allow us to be able to read the values easily. Now we move it to an edge, we get a different reading. Here we are getting somewhere between 58 and 59. And finally, we move it inside the line. We get 62 as the reading. So in order to get the robot to recognize the correct position, or whether it's on the line or outside of the line, we need to do this calibration step first. Only after that, then we can develop the correct values for the line detection algorithm. Here we will look at the operation of the line follower robot. First of all, the robot is on this track here, given by the standard Next Retail Kit track, and we'll try to follow the track on in a counterclockwise direction. See its operation where it detects an edge and starts to move back towards the line in order to follow it. We need to be careful about the speed that we program the motors to operate at. If it's too fast, it's possible that the robot will overshoot the line and escape into unknown territory. Here we see what happens if the robot is outside the line. It tries to recover, but it's not always guaranteed that the algorithm we use will allow us to reacquire the track all the time. So far so good. If we cannot find the line, we will try to acquire it by rotating in place. However, since there is no valid line in this section of the track, we will go in a circle indefinitely. Here he has managed to reacquire the line after spinning through part of the track. That's all. These are some references that you can look at for further information. See you next time.